Hello, this talk is about the contribution of artificial intelligence technologies for extracting value from data modeled by graphs. So who we are, my name is Maria Dofo, so I'm the CIO of DataVest. I have a PhD in computer science, and Mehdi Jelabi is data scientist. I also have a PhD in computer science and applied mathematics, and he worked on graphs. So DataVest provides both consulting on the entire data value chain. So this ranges from the emergence of use cases to the recommendation of concrete technical architecture and the development of data science, algorithms, and innovative artificial intelligence solutions at the state of the art. DataVest's vocation is to develop cutting-edge technologies, integrating research results by designing and implementing innovative methods and algorithms. So DataVest has also been awarded the Young Innovative Company label in 2016, and the R&D work initiated since the creation of the company has yielded promising results applicable to many use cases. So the agenda of this presentation is the following. So we are going to talk about the context and define the variety of graphs. Then one important point is to build graphs. So how can we build graphs? And then what can we do with graphs? Which algorithms can be used? And then we'll see two use cases. The first one on recommendation and the other one on fraud detection. So graphs are a data structure allowing the most intuitive representation of what we call complex systems with many possible use cases. So we have a list of potential use cases in this slide. For example, the detection of abnormal behavior can be applied to fraud detection and anti-money laundering, cybersecurity, or intelligence. So objects can be represented by nodes in the graph, and links can represent fraudulent or non-fraudulent transaction, for example. We can also use graphs in human resource, for example, for identifying talent and build cohesive teams, or to predict career path, or to recommend training, for example. And safety are also potential use cases. For example, you can study the social interactions in the context of the health crisis. Of course, mobility for decision making is also a potential interesting use cases, as well as supply chain, for example, to spread information and alerts to the entire production chain. You can also use graphs for client interaction analysis or in the legal sector. So as you can see, there is many potential use cases that can be used with graphs. So the variety of graphs. We can vary from simple graphs to more complex one. For example, the bridge of Königsberg was the first representation by graph. So the idea is that we want to cross the city and cross the bridge only once to go from one point in the city to another point in the city. So this is a more simple representation. So in green, you have the city, and then in blue, the river, and then you have the bridges that cross the river. And then the idea was to represent that by simple graphs. So here you have nodes representing the green part, and then the links between nodes represent the edges. So the answer was no, it was not possible to cross, to work on other parts of the city. Crossing the bridge is only once. So now attributed graphs are an example of more complex graph, for example, Facebook. So in this graph, you have only one kind of relationship, which is someone knows someone else, but each person, so each node, is characterized by a set of attributes. A more complex case is heterogeneous graphs and multiplex graphs. So in the case of heterogeneous graph, you have different types of nodes, links that can coexist with a graph. And in the case of multiplex graph, you have different types of links that can connect the same pair of nodes. And in the real life, graph often combine all these properties. For example, in the case of the interaction layer, you can have multiple nodes and multiple relationships, and you can have information attached to nodes and relationships. So in this case, you have a trade-off between information accuracy and graph complexity. So in this simple schema, we represent the variety of graphs, simple, attributed, heterogeneous, multiplex, and we just show that the intersection between all this variety of graphs correspond to very complex graph with accurate modeling, but this leads to a high level of complexity for applying machine learning, graph machine learning algorithms on this kind of graph. So how to build graphs? So the way you define the graph is decisive for the task that you will be able to apply on the graph. So you have to answer two questions. What does a node represent? Do I have complex nodes, very different kinds of nodes? Do we have some information attached to the nodes or not? What do the link represent? It can be explicit links that you have in the data, but it also can be implicit links that you will be able to infer. So the data is not necessarily as modeled in your databases, so the representation is not always unique. So just giving an example from a classical relation database. So here you have employees, departments, projects, and for example, between employee and project, you have the relationship works on. So these are explicit relationships. So you can have nodes corresponding to employee, nodes corresponding to projects, and a relationship between employee and project, which is works on. So this is represented here as the green links between nodes. But you can also infer some other relationships from the content of your database. So here, for example, you have two employees, and these employees are working on the same department. So you can infer a relationship between these two employees, which is same departments. So here is an example from a research paper, and the way you can represent graphs from an example. So at the left part of the slide, you have the more complex representation. So you have nodes with content attached to the nodes, and you have 4 different relationships between users and items. So if you want to represent a simple graph, this is at the bottom of the slide. So here you keep only your nodes without any information attached to the nodes, and you put a link where there is a relationship, whatever relationship is it, between these two objects. So you obtain a simple graph. In the middle, you have the same graph, but you consider other relationships that can appear. And then at the top, you have the more complex representation with all the multiple relationships and also all the information attached to the nodes. So now what can we do with graphs? We can do some graph exploration with basic statistics on graph topologies, like density of the graph, betweenness, closeness, and so on. You can also summarize graphs based on links and or nodes to perform clustering, community detection, or even aggregation if you want to see a reduced view of your graph, for example, for visualization. And you can also apply machine learning to graphs with graph neural networks for link prediction and node or graph classification tasks. And you can also do graph shallow embedding. So we will mainly talk about graph machine learning, but a few words on graph exploration and summarization. So there is many possible measures that can qualify your graph. For example, the importance of a node in the graph or the topological properties of your graph. So for example, the notion of centrality. So being central means for a node that it's being the source or destination of many relationships, which we call the degree centrality, being close to many actors, which is called closeness, or being at the center of many connections, which is called betweenness. You can also compute the degree of your graph, the clustering coefficient, and also the density. You can also extract many information from the topology. So if you consider the schema with nodes in orange, white, and purple, and many relationships, you can easily infer that, well, these nodes represent persons in a company and the people they are interacting with. So if you consider the node in purple, you see that he interacts with many different groups in the company, and the node in orange interacts only with its group. So you can infer that the node in purple will probably be more innovative and get more ideas because he interacts with many people. In the left part of the slide, you also have a graph with clusters in orange, yellow, gray, blue, purple, etc. So if you consider a use case in which you want to recommend articles or newspapers, etc. For example, you have two different clusters here, gray and blue, which are not really well separated. So you can also infer that you will probably be able to recommend some articles in blue to people reading articles in gray. For example, if it corresponds to domains that are closed, for example, computer science and mathematics. And then in orange, you have another cluster which is very well separated, for example, retail. And it will be difficult to recommend some articles from this for people reading this article in this cluster to other domains. Graph machine learning, you have different tasks. The first one is a task of node classification. So you want to predict the missing label of a node within a heterogeneous graph, for example, a fraud label. You want to determine if a node is probably fraudulent or not. The link prediction task, you want to infer existing knowledge, either to complete the graph, for example, adding missing links, or to recommend new links. So the most scient application is the recommender systems. And graph classification, in this case, in this task, you want to assign a class to the graph. So an example of application is the identification of toxic association of drugs in a labeled set of molecules represented by graphs. So here is a schema representing the different tasks. So in blue, you have the explicit relationships in your graph. So you have individual competency trainings and needs expressed by companies. And then you can infer some relationships And also you have implicit relation, for example, similarity. You can define similarity between users and similarity between trainings. Or you can also predict the label of a node. So now the graph representation. So the most common graph representation before the deep learning techniques was the adjacency matrix. So you allow a graph representation without loss of information, but the problem is that the matrix is sparse. So this motivated the task of learning low-dimensional embeddings of nodes, and the idea is to map node to embeddings such as similar nodes in the network are embedded close together to reflect the node similarities in the original network. So you have to define the similarity. So if you want to learn a representation, you have two different paths to do it. So you can see the input graph. So in this is a complex graph with many different relationships, and you also have feature attached to the nodes. And then you want to produce node embeddings, taking into account the topology of the graph. So you have two different ways to do that. The first one is called shallow embedding. So you use techniques like matrix factorization or random walk to integrate the topology in the features. And the other one is from graph neural networks, and it uses message spacing between the different nodes. And then you can obtain nodes embeddings, and then with these embeddings, you just need to define the prediction aids. So you have many prediction aids. So task at the node level. So you use node embeddings. At the edge level, you use pair of node embeddings, and at the graph level, you will use all the node embeddings. So shallow embedding is unsupervised, and in that case, label and feature information is not exploited. And graph neural network are supervised. Node and edge feature are taken into account. The first one, shallow embedding, is transductive, so you need the entire graph during node embedding generation, and graph neural network is inductive, so you are capable of generalization, so you can induce the embeddings of unobserved nodes based on their position in the network. So if we consider the two different use cases, so the first one is about content recommendation. So the business challenge was to be able to make cross-cutting and relevant recommendation between different universe, so taking into account article of newspapers and events that are organized, or job boards also. And all this information was in silos, so the idea was to break data silos and also to engage and retain clients by providing useful recommendation for them. So the artificial intelligence solution that was used was based on building a graph and then apply graph machine learning techniques combined with natural language processing, because we have some textual elements attached to the articles or events, and then to provide content recommendation. So before the project, there was no ability to link content. They got manual rules provided by the business units, and it was impossible to cross content and sector of activity. So after the project, so the representation with graph, beyond the similarity of the content, makes it possible to take into account the neighborhoods to provide more relevant recommendations. So this is a brief overview of the projects, 3 different steps. So the first one was to build the graph. So by highlighting the relational structure of the data. So we built 3 different graphs, graph with tags that were attached to the different elements, to articles and events and so on. The links between documents, so we have some links to similar documents in the database, and also user clicks. And then we aggregate all this information to build one graph. So the second step, we use 2 different approaches to compute the similarity of documents and to make recommendation. The first one was only a graph approach, so the similarity was computed only on the graph, and the other one did not use any graph. It was only natural language processing approach, and due to the restriction of time we had for implementing this project, we used a very simple way of representing our documents with topic extraction. And then the third step that was interesting was to integrate events data and also build a graph containing articles and events. And then we apply the graph approach with natural language processing for the recommendations. So the nodes were represented by vectors extract with a topic extraction algorithm. And then we use a link prediction algorithm to make the recommendation. Another use case is the detection of fraudulent transactions. So this use case is particularly complex because data are highly dynamic and also highly imbalanced. We have very few fraudulent transactions. So we have to determine the task we want to perform on it. It could be classification of nodes, so give a fraudulent label or not to a particular node, or prediction of links, so to predict fraudulent transaction. And the graph can capture local and global information of an individual or an object within a network. So this part is really interesting and very different from the machine learning, the classical machine learning approach on this use case. So the possible approach, you have 3 different approach possible. So the first one is a classical one. So you train a classifier on a set of relevant features defined by business experts. So you don't have any graph here. The second one, you perform only graph machine learning. So you consider it, so you learn representation embeddings on the graph, and then you use the tasks of node classification or a prediction of links. And the third one, which is interesting in this case, is the feature engineering part. So you have on-craft features, and also you can learn embeddings from the graph. So you learn embeddings and adding the topology of the graph in these embeddings, and the combination of classical features and feature learn on the transaction graph as input of a classifier compatible with unbalanced class produces the best results. So the main advantage is that it does not replace the solution in place, but contributes to improve it. It's an adductive approach. We have generalization capacity. You have many possible choice for the graph approach that could be compatible with the data. And then this approach is scalable, which is also very important. So if we continue with this example of combining graphs and machine learning for detection, so we are in the third case that we previously mentioned. So you can calculate the classes that correspond to credit card user profiles, then identify cluster of illicit transactions and associated behaviors, and then you can use graph to infer and propagate fraud susceptibility scores, and then use computed classes and score as a new learning variable and train classical machine learning models to improve the accuracy. So as a conclusion, we have specific graph machine learning techniques that can be used alone or in complement to other machine learning techniques. This takes into account both the content and the structure of the graph, so the neighborhood. We have many potential use cases that can be represented by graphs and that can benefit from the algorithms that can be applied on graphs, so exploration, clustering, or machine learning graphs. But we have also to think carefully beforehand about scaling up and building the graph. So how we build the graph is very important for the task we will be applying on then after. And this also requires development from existing libraries. So thank you very much for your attention.